Good morning, good afternoon, as the place you are in. Welcome to the 17th Afomp monthly webinar. Continuously, we are doing since June 2020 every month, in addition to our Afomp school webinars of around 2 to 3 hours. So today, the topic of the webinar is image-guided application in radiation therapy. And the speaker is Professor Tae-Suk Soo, a very renowned medical physicist and the professor of medical physics in Korea, the immediate past president of the Afomp. He has hugely contributed to the Afomp. Today's moderator is Dr. Michael Lee from Hong Kong, and I briefly introduce him. He has kindly accepted to moderate this webinar, and he is the president of the Hong Kong Association of Medical Physics, senior physicist at Pamela Yonde Nethersole Eastern Hospital, Hong Kong. He is also adjunct professor of nuclear and risk engineering, City University, honorary assistant professor, Department of Diagnostic Radiology, the University of Hong Kong. Without spending more time, I hand over the floor to Professor Dr. Michael Lee to conduct the webinar by introducing Professor Tae-Suk Soo. I unshare it, and the floor is yours, Dr. Michael Lee.
Thank you, Aaron. Just do my screen sharing. So thank you very much, and welcome everyone. We're sorry that we couldn't do it last week. But anyway, welcome to the 17th AFOMP webinar. The topic today is image-guided application in radiation therapy. Before we start, I'd like to remind you all to turn off your microphone and videos so we can have a good bandwidth for today's event. And if you have any questions, please put them in the chat box. There will be a Q&A session after the talk. I'm sure you all understand the importance of hitting the target accurately in radiotherapy, and for that, we need patient image data to do the planning and to steer our radiation beams. And many imaging techniques have been developed. To use these techniques and technologies safely and effectively, you need to understand how they work, their strengths, and their weaknesses. So today we're very happy that Professor Tae-Suk Soo is here to tell us about image guidance and the application in radiation therapy. Professor Soo is currently the Professor of Biomedical Engineering of Catholic University Medical School and the Director of the Research Institute of Medical Engineering of Catholic Research Institute of Medical Science in Korea. He is also the honorary chairman of the Korea Society of Medical Physics for Radiosurgery. Professor Soo studied nuclear engineering in his bachelor degree and obtained his PhD in medical physics at the University of Florida. He is both an engineer and a physicist, combining the best of both worlds into medicine. His special interest and actively published in radiotherapy techniques and technology, the software and hardware development, radiation detectors, quality assurance in radiotherapy, even boron neutron capture therapy, proton boron fusion therapy, MRI, Monte Carlo simulation, and recently the application of artificial intelligence in radiotherapy. He contributed greatly to the development of radiosurgery, and in 1998, he conducted the first radiosurgery using FFF beam on patients at St. Mary's Hospital. He also pioneered many technologies, including a radiotherapy drum playing system and 3D active shield magnetic resonance imaging. Throughout his career, Professor Soo has received many awards, including the IOMP International Days of Medical Physics Award last year, 2016 AAPM Science Council Section winner, and the IOPM Award of Outstanding Contribution over the last 50 years. 2018 IOMP Plaque of Appreciation, 2018 AFOMP Plaque of Appreciation, 2017 Editorial Board of Medical Physics Plaque of Appreciation, also 2006 Best Research 50 Awards of Korea Science and Engineering Foundation, and numerous Best Papers, Posters, and Presentation Awards. As Aaron just said, Professor Soo has also served in many international organizations. He was the chair of the IMPCB Registered and Record Committee and the chair of IOMP Publication Committee, and he was the past president of AFOMP. He was the editor of the Journal Medical Physics for 10 years and is still serving as the editors of many other renowned journals, including Physica Medica, Medical Physics International, the APESM from Australia, and Journal of Radiation Physics and Technology. Professor Su has been vigorously promoting development of medical physics in Korea, in the Asia-Oceania region, and in the global community. He organized the World Congress of Medical Physics and Biomedical Engineering in 2006, the Asia-Oceania Congress of Medical Physics 3 times in 2002, 2006, and 2012, as well as the International Stereotactic Radiosurgery Society Congress in 2009. He's published over 300 peer-reviewed papers and more than 1,300 proceedings. Today, he supervises or directs many frontline research projects in radiotherapy and radiosurgery technology. Without further ado, let's welcome professors to the stage. Thank you very much, Professor. The floor is yours now.
Okay, thank you, Dr. Michael Lee, for the kind introduction. First, I would like to thank the organizer of Afomp webinar for inviting me here and organizing this wonderful seminar. I would also like to thank Professor Aaron Chogley, President of Afomp, Afomp ExCom members, and all the delegates for joining this seminar. Today, I'm going to talk about image-guided application in radiation therapy. An article that explained the necessity of image-guided radiation therapy, what we call Igct, was published in Nature in 2012. There are many image-guided applications in radiation therapy. In this lecture, I would like to discuss some image-based technology developed for radiation therapy. 3 kinds of imaging modality are used in medical area for diagnostic imaging and treatment. Static, single imagery, and multi-modality imagery, and 4D imagery. Previously, static single imagery have been used to define tumor using CT, MRI, or PET. Recently, the multi-modality imagery have been utilized in medical area to define tumors and functional change and more accurately using PET-CT or PET-MRI. And 4D images have been also applied to localize moving target accurately, especially in radiation therapy. So in this presentation, I will rather focus on the application of multi-modality images and 4D imaging in radiation therapy. So first, multi-modality imagery. Before I talk about the application of multi-modality images in radiation therapy, I would like to show some of the application used in diagnostic imaging for investigating the tumor definition and functional change. So this table shows the typical characteristics of CT, MRI, PET. So we are familiar with these 3 images, but a CT is generally good for obtaining a suitable for obtaining an accurate localization without distortion. Also, CT is good for dodgemetry because the CT number is directly correlated with dose computation. MRI is good for obtaining a especially detailed morphology, showing good tumor detection in soft tissue. And PET is better for evaluating the pathology and detecting staging and malignancy. So if we combine these image modalities, we can obtain the whole advantage of each image. So when we combine anatomical images such as CT or MRI with biological images, the PET, SPEC, and MR spectroscopy, then we can generate the hybriding imagery, that is multimodality images, the PET CT or PET MRI. These multimodality images are very useful for investigating tumor definition and functional change of the regions. Here is one example for defining a tumor using PET MRI. So, although PET image is unclear, however, the target is well defined, especially in the PET. So when we fuse this PET image with the MR, we can see the target clearly from the PET and nice morphology in MR image. So this PET MRI is very useful for defining a target with a nice morphology in other areas. Multi-modality images are also very useful for diagnosing neurodegenerative disease such as Parkinson's disease or Alzheimer's disease, especially using PET MR or SPECT MR. So I will not discuss detail this issue here. Maybe you can refer to the previous my publication for more information. And this shows a multi-parametric mapping based on functional imagery. Generally, in MR imaging, high-grade glioma indicate a high blood flow rate. In RCVB, regional cerebral blood volume map, and a low diffusion coefficients in ADC, apparent diffusion coefficients map. So we can localize high-grade tumors because the high value is clearly presented for this region, is a red region, through these multi-parametric mapping procedures. I will not discuss detail, but there is some conversion of the images, then we can easily find some glioma representing the high value of the signal. Therefore, the multimodal and the post-processed images are used to determine the high-risk tumor volume in high-grade glioma. As you see in this figure, we can extract malignant residual tumor volumes on ADC maps through many various, step of the mapping techniques. So now I am going to discuss the application of multi-modality images in radiation therapy. CT is generally used in radiation therapy because the dose is directly correlated with the CT number. MRI and PET are also used to define tumor more accurately. This shows dose distribution on combined CT MR images. This multi-image is very helpful for confirming the radiation coverage in radiation therapy. And this is another example of utilizing multi-modality images in radiation therapy. This figure shows the the tumor shape of non-small cell carcinoma. This left figure, in left figure, the target is shown blue and green line using the soft tissue and lung window of the CT. In right figure, the target was shown by red line, which is more accurate and more smaller, with a 30–60% reduction in PTV, and which is quite good to minimize radiation dose to normal structure. Recently, biological radiation therapy techniques have been developed using the multifunctional images. Biological RT techniques include software to analyze functional imagery, analysis of biological parameters based on multifunctional images, and mapping of the biological parameters on tumor volumes. And this slide shows our research for applying various functional images and molecular imaging to evaluate radiation therapy effect. And this shows some radiation effect using the molecular optical imaging system. There are many steps here. Actually, we collaborate with the molecular imaging team at Stanford University, MIPS, to evaluate the radiation treatment effect on memory carcinoma cancer cell using multi-modality molecular images. So before we apply multi-modality imaging to human, it's very important to evaluate the registration algorithm using human phantoms. So this shows whole procedure for evaluating the registration algorithm using the phantom. The first, we developed brain and lung phantoms for CT, MRI, and SPECT. And then we acquired the image and registered the image of phantom using registration algorithms such as chamber matching or mutual information, and fused the image of phantom and evaluate the registration algorithm. If the error is within the acceptable range, then we can apply multimodality image to human. So most of the imaging error was 1 or 2 millimeter, which is acceptable in medical imaging. So now I'm going to talk about 4D, the application of 4D images in radiation therapy, especially image-guided radiation therapy. So image-guided radiation therapy, IGRT, is based on following 4 steps: localization, planning, and verification, and delivery. IGRT also requires 4D technology for each step. So I'll briefly discuss 4 steps of IGRT and show some recent research which we did. So first, localization. The localization of the moving target is based on either respiratory signal or image guidance. Respiratory signal is used for gating the radiation beam. So we can obtain the respiratory signal using various sensors such as a spirometer, some ester, or in the bell transducer. And CCD camera is also useful to confirm the position. This diagram shows the entire procedure for developing a multiple respiratory signal acquisition system using various sensors for the correlation study. As shown in this figure, the signal from the bell transducer was well correlated with the fluoroscopic patient data. This is real data. As well matches, and the correlation graph is very nice. That means the respiratory signal is well matches with the real patient target. So we can easily use respiratory signal as gating. When we gate the beam, this is one of the possibility for us to treat the patient. And this shows the multiple respiratory signal acquisition system that we developed some long times ago. This system can analyze the respiratory signal obtained from various sensors, spirometer and CCD camera. This system is very useful for verifying the accuracy of a respiratory signal by comparing each other. As you see in this figure, two signals show same patterns, which seems to be very reliable. So if there is some mismatch, then there is some problem. This slide shows the updated respiratory guidance system under abnormal compression. This developed system consists of abnormal compression pad, gas pressure sensor, and visual biofeedback device. So we expect the system provides the quality of respiratory motion management because of its capability of providing a real-time surrogating signal on the compression and enabling visual biofeedback. So image guidance is a direct method for localizing a moving target. So although 4D MRI and 4D PET are used to evaluate the motion of the target, 4D CT is typically employed to obtain a more accurate localization of a moving target. In past years, cone beam CT has been used to localize the target in radiation therapy. But recently, the inverse geometry computed tomography, what we call Igct, 4D Igct, with a multi-source and a small detector has been developed to overcome shortcoming of cone beam CT, such as scattering problem and cone beam artifact. So to exploit the advantage of Igct and reduced respiratory motion artifact, we investigated the 4D Igct imaging method for radiation therapy. I'm not going to discuss this method in detail here. You can refer to the paper published in PMB this year. So you can see the whole method, how we can develop the 4D IGCT, how we can apply this system to evaluate the scatter and respiratory artifact. So as you see in this figure, the 4D IGCT had a uniform image intensity. It's very uniform. Although 4D cone-beam CT did not. There's some fluctuation. Also, IGCT also produced less scatter and less cone-beam artifact. Therefore, IGCT could be good for the localization of the moving target and radiation therapy. Okay, let me introduce more image guidance researches briefly for the localization of the moving target. We developed a respiratory guided 4D digital tomosynthesis to improve image quality and reduce imaging dose. So you can also refer to this paper published in PMB for the more detailed information. So because of limited time, I will discuss in detail. I just introduce some image guidance localization system. Dr. Yamamoto team at UC Davis developed a pulmonary functional IGRT, which is very good to evaluate lung localization using the 4D ventilation imaging. Also, I will not discuss in detail here. There are many information in the Journal of Medical Physics and Red journals for the pulmonary functional IGRT. Actually, we cooperated with the UC Davis for functional IGRT to develop 4D lung phantom using 3D printing to confirm pulmonary functional IGRT. And this work was presented in AAPM in 2017. And also this study was published in Medical Physics last year. Okay, planning. Okay, this shows the whole procedure of adaptive radiation therapy based on IGRT. Actually, 4D planning is very complicated and difficult to apply to the patients. 4D planning is required, especially for IGRT planning to evaluate the moving target. I will not discuss in detail all the procedure. However, we need to develop many advanced techniques to enable 4D planning. A few years ago, we actually developed some prototype of IGRT planning system. So I'll just introduce that prototype of IGRT planning system. So actually, it's not for the commercialization. We implemented many useful modules for IGRT study and corrected software and are still improving this system. We compared our plans from this system with the commercialized, recently commercialized RTP system for the clinical studies. Also, we have tried to implement AI and big data to investigate the possibility of AI-based RTP system. So this system is very good for the research. And we investigated the usefulness of 4D planning compared to the 3D planning. And this shows the study to evaluate dose in the target and normal tissue using 3D and 4D dose planning for liver SBRT cases. As shown in this figure and table, we confirmed a very significant dose difference in both target and normal structure. So we need 4D planning instead of 3D planning to evaluate dose computation accurately. The verification. The main concern in 4D verification is to check the position and dose of moving organs. The verification of a moving target is very difficult as the motion causes many variations. Generally, there are many uncertainties in localization, planning, and delivery, human error and machine uncertainties. So many uncertainties we need to consider. So it's very important to verify the accuracy with regard to each step, so localization, planning. So verification is very important. To test the moving target and verify the dose in the moving target, we developed various types of moving phantoms. So I'm going to show some of our development. And this is 1D, and this is some programmable 4D phantom. And this diagram shows the entire procedure for developing a moving phantom, including the body and internal organs. This shows the programmable nonlinear 4D moving phantom, simulating the real patient motion. So first, the 4D CT patient data were transferred to personal computer. Then motion control software was employed to control the moving phantom. And finally, this verification, the camera system can verify the motion of the moving phantom. So this system is very nice to check the dose and position of the organ of patients. And recently we developed 4D moving phantom to simulate internal tumor motion. And this figure shows a component of the 4D moving phantom, actually XYZ axis motion platform, and AC servo motor can control 3-axis motion platform, and Dodgemetry phantom and imaging phantom can be placed on the platform to estimate the position of the target and dose. To control the 4D phantom in the PC environment, a dedicated motion control software was implemented, and a model-based or clinical 3D body motion can be recreated using the developed software. So we tested a 4D moving phantom in linear room and assuming a real patient treatment. The result was good. In addition to 3D rigid body motion, actually, we need to consider deformable motion. So we developed deformable lung phantom. This is a prototype of the lung phantom. And we test and evaluate the deformable phantom. So we acquired the 4D CT imagery of a deformable phantom during breeding cycles, and then evaluate the deformable magnitude using subtraction, image subtraction method. And based on this phantom, we developed a more advanced lung phantom with UC Davis, which I already discussed previously. But I think it's still challenging to develop 4D deformable moving phantom to simulate exact deformable motion of the patients. This shows the film dodgemetry of a static target and moving target. It shows the planning for the static, and this is actually a measurement for the static and movement, 10 mm movement and 20 mm movement. So as you see in this figure, when the target move more, then we have more broad dose distribution. So we cannot use 3D planning to evaluate the moving target. So definitely we need a 4D dose plan. In IGRT, we usually consider large movement of the target. And then how can we consider very small or tiny movement of the target? For example, when we immobilize the patients still can move very slightly. So in this study, we propose a new verification system that uses tactile array sensor to verify very small and tiny movement of under the immobilization. So computer can evaluate and provide error map using a tactile array sensor. So this is very useful to consider patient alignment error even under the immobilization tool. Okay, so final delivery. So 4D delivery is very difficult. We can find out, the moving target and plan and verify. Then finally, how we can deliver the beam for the moving target. So actually 4D delivery is based on gating, which I mentioned already, or tracking. So in gating, we deliver radiation when beam is matches with the gating range here. So beam is delivered when the beam is matched with the respiratory signal. But in tracking, we deliver the radiation continuously while moving together as target move. Actually, patient is move according to the respiratory, but this CyberKnife can also move as the target move. This is a tracking, very difficult. So tracking is a direct method, but it's very difficult to track a moving target. So I would like to show some research work regarding DMLC, dynamic MLC tracking, conducted in collaboration with the Stanford research teams a few years ago. So among the feasible 4D delivery solutions, dynamic MLC, DMLC, tumor motion tracking was introduced by Dr. Paul Kill groups. So this DMLC tracking is very nice. We quickly track the moving target. However, the tracking efficiency, if the target move is parallel with the multi-leap, it's okay. We can easily track. But if the target move perpendicular to the leap direction, then it's very difficult. So the main concern of our research is how fast the DMLC can track a target motion, even in the case of the perpendicular leap direction. So the tracking efficiency is limited by multi-leap collimator mechanical constraint, especially for fast tumor motion perpendicular to the MLC leap travel direction. So as you see in this figure, the efficiency is decreasing as the movement is faster. So the efficiency is low. So how we can improve this efficiency? So as an alternative solution to real-time tracking, we investigated the moving average tracking. And this slide shows a schematic of the moving average tracking study. This whole work is performed as collaborative research with the Paul Kills group at Stanford. And the moving average tracking algorithm was implemented in this system, especially DMLC tumor tracking system. And using the 4D phantom, the moving average tracking performance was evaluated in terms of three efficiency: delivery efficiency, and geometric accuracy, and dodgemetric accuracy. So in result, all the efficiency were improved when we apply moving average tracking rather than real-time tracking. Actually, these two guys were my PhD students, and this is the Paul Kill, who is now in Sydney University. And this work was published in Medical Physics Journal. Okay, in summary, the analysis of multi-modality images such as PET-CT or PET-MRI and image registration provide useful information for delineating the target volume for radiation therapy planning. A more reliable definition of the local tumor volume lead to better definitive local control through clinical studies. We need biological imaging tools for the better definition of the tumor volume using various multi-modality and multifunctional technique. We need to develop a more accurate time-resolved 4D localization technique for modeling the intrafraction organ motion using 4D imaging technique. We should develop new 4D radiation treatment planning, possibly AI-based in the future, and delivery schemes incorporating the motion deformation of the organ. Definitely, we need an accurate verification system for dodgemetry and motion and using a 4D moving phantom. Okay, finally, I would like to thank all the colleagues who support this presentation. Thank you very much for your attention.
Thank you, Professor. I have a question here from an audience. Could you summarize the current status of confidence in PET images as the definite modality for defining functional target volumes in a dose painting setting? Or a simpler one, please, if you consider the remaining uncertainties in PET quantitative imaging and target contouring.
Okay, is a question?
Yeah, that's a question, yes. Well, actually, he's asking you to summarize the current status of confidence in PET imaging as a definite modality. Say, if you can use PET as a definite modality for defining the functional target volumes in a dose painting technique.
It's a very good question. Probably some radiologists may the answer well, but usually the PET shows some a stage of the cancer and also some more region of the tumor. So I'm not quite sure because I'm not a doctor, but usually the doctors favors to use PET with the CT. But CT and MRI is good to see some morphology, but PET is very nice for the pathology. Usually in medical area, most of the doctor wants to use PET together with the CT and MRI. Maybe I think some clinical doctor can answer, and actually the radiologist can answer more better than me.
Yeah, I think Amin would like to know if how accurate you think we can use the functional. We can use the quantitative information in PET to actually define the accurate boundary of the target volume, perhaps, or the accurate boundary for those for boosting, perhaps, because we all know that quantitative PET has got some uncertainty in it. Yes, actually, we did. The PET shows some the quantitative the value. So our colleagues used some quantitative values to evaluate some boundary and real tumor, and also we checked some quantitative value with the real your cancer stage. So some of our research was published, but it depending on the disease. So I think your comment is very important for us to evaluate the PET imaging using the quantitative analysis. Thank you. There's another question about using dynamic MLC for tumor tracking. Is it effective clinically? Yeah, that's a good question. Actually, the DMLC was introduced by the Professor Paul Cares a long time ago.
I saw that system when I visited Stanford University. He showed those, the prototype of DMLC system and his group, and they tested. But I'm not quite sure, whether the DMLC can work well in real clinical stage. But in theory, it works very nicely. That's why maybe some vendor can apply DMLC system and modify and also some improve the function of the DMLC, especially as I mentioned earlier. DMLC can track easily the motion, the moving target when the motion is parallel with the lip direction. However, if the motion is perpendicular to the lip direction, the efficiency is very low because it's not easy to track the motion. So that means that's why we can use some average concept. So if we utilize this DMLC more accurately, the question is how fast we can track the DMLC, track the motion, target motion using the DMLC, even for the perpendicular case. So I think the most important thing mechanically, two ways. If we want a real-time tracking, then we should solve this problem. Otherwise, if we want to use some average comps, maybe improve some part of the efficiency, then we can use the average motion tracking system, which we started 3 years ago. So I think we need to improve, and also it depends on vendor, and there are some still need to improve some tracking system.
Right, I've got another question which I'm not sure if I understand. Actually, it says for IGLT, would the treatment planning time be increased? And what about the dose amount while planning and delivery?
Yeah,
would it be more conformed?
It's very good question. Yes, so I think still in our hospital also, the most of doctors use 3D planning instead of prototype of 4D planning. It goes very time consuming, and still we need to verify many, the techniques, as I mentioned before. So still challenging, I think. So maybe we need to find out a very fast dose algorithm to be used in 4D planning. Also, we might use some pre-plan using the big data. So I think in future, AI-based, the RTP system could be the one solution to be used in clinical area.
Right. Okay. There's another question about using different imaging modality in Ct Simulator. We use a flat panel, just like the Tumor machine, just like the Linac. In MRI and PET, usually they use round couch table. So during image fusion, the Ct MRI or PET CT, there could be internal organ movement and localization problems, especially with nearby organs. What would be the uncertainties?
Yeah, it's also a very challenging question. Actually, it's easier for us to fuse, that the static target is okay to fuse MR with a PET or CT. But if the target is moving, how we can find out some, the correlation between the 4D PET or 4D MRI and 4D CT. It's really challenging, but we did. One time, we developed some 4D CT and MR PET to check some motion of the blood. Then we tried to fuse 4D images together using the 4D CT and 4D PET, but the result actually wasn't good because the error is we saw some, you know, the unreasonable error. So I think it's still challenging for us to fuse a moving target using the 4D CT and 4D MRI. So I think we need to improve, and we need to solve how we can find out the good solution for the 4D multimodality images.
Well, for that, I just have a question myself. How about, because I know you're working on using artificial intelligence in radiotherapy. I'm just wondering if that can help us solve the problem with all these deformable registration in different modalities. The use of artificial intelligence.
Yeah, actually, we used some registration algorithm, such as very the prototype of image registration algorithms, such as chamber matching and mutual information. But I think there are more some advanced image registration algorithm. But previously, I saw some study when we started, you know, evaluated the moving phantom for the multiple imaging system. Then we used the chamber matching and mutual information. However, if we apply some more advanced image registration algorithm, I think there will be more accurate result for the matching the two images.
I think the time is about up. So let's end the session, and I'll hand over to Aaron.
Yeah. Thank you, Dr. Michael, for nicely conducting and moderating this webinar, collecting the questions, putting to Professor Tae-Suk, and getting the answers and the discussions. Thanks to Professor Tae-Suk for your excellent talk and the work you are carrying out your group. It was very, very nice talk and information. So we had this 17th webinar, which was really supposed to be last week on Thursday, but because of some technical problem, we rescheduled it for today, that is a Friday. And thanks to Dr. Michael Lee for moderating. Thanks to Professor Tae-Suk, all the participants. As you know, Afomp is organizing regularly the monthly webinars as well as the Afomp School. And the 5th Afomp School will be on 23rd October 2021 during 6:30 a.m. GMT to 9:30 a.m. GMT. The link is already available on the website, circulated to all to register, and this will be on the dosimetry and quality control in diagnostic radiology. And there will be 4 speakers. Professor Anupama Azhari from Bangladesh, she is the Secretary General of the Afomp. Then Jaya Sungtham from Sri Lanka. Then Catherine from Germany, Ghulam Abu Zakaria from Germany, and the topic of the speaker this. So please do join by registering yourself. As you know, continuously. So next 11th November, we have the Afomp webinar, and that will be on the augmented role of the medical physicists in radiation emergencies. The nuclear and radiological emergencies, the medical physicists can play a huge role, and that will be delivered by Dr. Brad Castles from Australia, and it will be moderated by Dr. Mansoor Naqvi from Pakistan. And as you very well know, that AOCMP 2021 is being held in Bangladesh, Dhaka, during 10th to 12th of the December, and this is in a hybrid mode. Daily I see today Bali is open for the tourist. Thailand is open. Many countries are getting open. If you are vaccinated and there's no quarantine required, I'm hoping that Bangladesh also by November, they will come out with the new guidelines. No quarantine may be required. That is what we are presuming as many countries. So there is an opportunity to attend in person. Even if you cannot do that thing, virtually you can attend. For virtual, the registration fee is very, very minimal. We have got more than 150 abstract. We have got many invited speakers, talks, and so many things. So this will be a great opportunity to meet each other in person, discuss the things. So these are the opportunities. So please do visit AOCMP 2021 website. All the details, they are there, and try to participate. If you come in person, very good if you permitted. If not, at least virtually. Afomp is doing a lot of other activities, and they have started many awards. So please keep on visiting the Afomp website. Afomp newsletter will come out, will be finalizing in the last week of this December. So please do submit your article information so that it reaches to the many medical physicians all. With this words, the recording will be available within 1 or 2 days on the Afomp website. People who could not attend, they can, or even who have missed to continuously go through this webinar, they can. Once again, thanking Professor Taisuk Su and his entire team for excellent presentation, Michael Lee for nicely conducting, all the Afomp, XCOM, Jin Xians and his team for organizing the Chapong as a PRC chair, for taking care of the actually accreditation, other thing, Rajini Verma for circulating, each one of you thanking with this thing. I thank all of you and say goodbye to all of you. Have a safe stay. Look forward to meet you during this Afomp's school webinar on 23rd frequently. And then also would like to see you during the AOCMP 2021 at Dhaka, Bangladesh. 2022 will be in Taiwan. The website we are going to launch soon. So have a nice time. Bye-bye. Thank you very much. Thank you very much.
Bye-bye. Thank you, Arun and Michael. Bye-bye.
Thank you. Bye-bye.
Okay, thank you.